because of some remarkable advancements in the field of optics, it has become possible to improve the quality of images from ground-based telescopes, from telescopes that are situated on Earth. And that technique is called adaptive optics. Okay, I want to spend 2 minutes talking about adaptive optics because I'm sure you'll find the science behind it very fascinating. So adaptive optics is a technique where we correct for the deformities in light produced by the atmosphere in real time. So it's like a real-time correction to the deformities that happen to light that is passing through the atmosphere. Okay, so you correct for it, and so it's like, you know, if you don't have a good 6x6 vision, you put on these prescription eyeglasses, and suddenly everything looks sharp, everything looks very clear. That's exactly what adaptive optics is. So the technique is very, very fascinating. This video shows it. So what happens is, here is a picture of a telescope, and it's situated inside a dome. And in adaptive optics, what they do is they fire a laser beam into the sky from the location of the telescope. It's a very, very powerful laser beam. So the observatories which have this adaptive optics technology connected to the telescopes, they will switch, once the adaptive optics is switched on, the laser beam is fired into the sky. So it goes up into the sky, and about 90 kilometers above the Earth's atmosphere, there is a layer of sodium that is present everywhere throughout the Earth, about 90 kilometers in the Earth's atmosphere. This laser will go and excite sodium atoms in that layer. And when the excited sodium atoms will start glowing, like the sodium vapor lamp that we have on street lights, the excited sodium atoms will start glowing, and it will produce an artificial star in the sky, as you see in this video. This artificial star is what is observed to understand the distortions or the deformities that are happening to light as it passes through the Earth's atmosphere. Okay, so this artificial star is created very close in the plane of the sky to the real star that we want to observe. So we want to observe a particular star, and what we do is, just pause the. What we do is the laser beam will create an artificial star very close to the patch of the sky where you want to create this, where you want to observe a real star. And this laser guide star's distortion is what is used to understand the level of distortion that is happening to light. Okay, and that distortion is measured by a control system unit that is connected at the back of the telescope. That is what is shown here. Okay, so I don't know how well the video is streaming at your end, but what I am looking at is the light coming in at the back of the telescope, and the light is getting recorded on a CCD camera, and finally you see a digital image of it. And if the atmosphere is there, because of the turbulence, the wavefront is getting distorted, the light is getting distorted. So as this animation shows, you can see that the light is distorted here. Okay, so adaptive optics is not switched on yet, but now you're going to switch on the adaptive optics. The circuit is on, and so the mirror from where the light is reflecting, that will change its shape in real time, and that changing shape of the mirror causes the light the light to get corrected for the distortions that is produced by the Earth's atmosphere, and the image becomes very sharp. So with the advent of this adaptive optics technology, it has become possible for astronomers to take sharp images of objects, of stars, etc. And using this technique, and with the help of large telescopes on Earth, it has now become possible to directly take pictures of extrasolar planets. So here is one example of it. HR 8799, which is written at the bottom, is the name of a star. It's just a catalog name. You don't have to worry about the number. And that star is what you see in the center. And using the Keck and Gemini telescopes, which are two big telescopes on Earth, and which both of them have adaptive optics in it, astronomers took a very high resolution image of that star And what they did is in the processing of that image, they subtracted the light from the star. That's why at the location of the star, you are seeing like a dark circle. But when you subtract the light from the star and look in the region near to the star, we see 4 very small bright sources. Those are the ones that are labeled B, C, D, E. Each of those 4 bright dots are planetary companions to that star. They are planets revolving around the star. Okay? So what you are looking at here is a real image of a star and the 4 planets revolving around that star. Probably there are more planets, but in this particular image, they were able to detect only 4 of them. And how do we know that these are planets and not some background stars? So the same system, HR 8799, astronomers have been monitoring it for many years. So what you are going to see next is a real image animation. So everything that you are going to see is real. It's not an artificial computer simulation or something. Of data of this HR 8799 star planet system spanning 7 years. So at the bottom of it, if you see, it says 2009. And once I play the animation, you can see that the date shifts to 2016, slowly increases to 2016. So data worth 7 years, images of 7 years put together in the form of an animation. The animation is only 5 seconds long. Okay, so pay close attention. In the center, what you see as a dark circle, that is the star. So the light from the star has been removed, and the 4 faint dots that we see, they are the 4 planets revolving around that star. Okay, so I'll play the animation and notice what happens. That's it. The animation is only 4 seconds long. I'll play it again. So what we are seeing is, over a period of 7 years, we are seeing the 4 planets' position changing around the star. In other words, we are seeing the planets revolving around the star. So if you are an alien astronomer, let's say that you are an alien being living in some other planet, and if you use your telescope to look at our solar system from a distance of maybe 100 light years or something like that, we would see the planets of the solar system going around the sun very much like this. Okay, so we will see the planets of the solar system going around the sun as a function of time. So what we are seeing are real images of exoplanets. Here is one more example. Again, direct imaging of exoplanets. Beta Pictoris is the name of a star. That star is what you see as the black big circle in the center. The yellow star in the center is to indicate that that is the position of the star. And off to the right, you see a few pixels which are bright. So that is a planet that is revolving around the star. And once I play the animation, you can see that with passage of time, you see the planet's position changing related to the star. And that is because it is orbiting around the star. Okay. So from indirectly confirming the presence of planets using radial velocity and transit method, now we have entered a time when it's become possible to directly see extrasolar planets. Okay. So as I mentioned to you, 1995 is when the first extrasolar planet was discovered, and 25 or so years have gone by, close to 30 years have gone by. And in those 30 years, the number of planets discovered has swelled in number to more than 1,000. Okay. Currently, as of date, we know about the existence of more than 4,500 extrasolar planets orbiting around various stars in a short span of 25 years. So this histogram plot shows the number of extrasolar planets discovered every year. It's a cumulative histogram. So every year, whatever number of planets is discovered, that gets added to the next year. And so in 2020, this is a bit old, it's about a year-old plot. You can see that the number is more than 4,000, and that number is increasing. Every day, new extrasolar planets are being discovered around stars in our own galaxy, the Milky Way. So now the question is, if there are planets in such abundance, how many of those planets are Earth-like? Okay, we have discovered extrasolar planets. So the next step is thinking about the habitability of those extrasolar planets. Whether those planets have conditions that are conducive for life, that are favorable for life. For example, if you take our solar system, Mercury has a rocky surface, but Mercury is not a habitable planet. Okay, you cannot imagine life as we know it evolving into complex life forms on the surface of Mercury. Venus has a dense atmosphere, but Venus has a very, very high surface temperature, so Venus is also not favorable. So what we mean when we say Earth-like is a planet with a rocky surface, with a dense atmosphere. The atmosphere is very, very important because atmosphere plays a crucial role in the sustenance and in the evolution of life. And as far as life on Earth is concerned, it is heavily dependent on liquid water. The first life forms on Earth originated in liquid water, and all the life on Earth depends heavily on the presence of water in abundance in liquid form. So when we say Earth-like, we are talking about a rocky planet with a dense atmosphere where water can exist in liquid form. Is it possible to infer for these exoplanets whether they are Earth-like or not? Okay. Now, obviously, it is not possible to travel to these extrasolar planets because with the current propulsion technology, if you launch a spacecraft, it is going to take hundreds of thousands of years to reach even the nearest star. Okay? So what to talk about stars that are very far away? It is